Hey there, welcome to AI Unplugged, where we explore the technologies shaping our future. I'm your host, Nova, and today we're diving into something truly fascinating that's happening at the intersection of neuroscience and computing. Have you ever wondered why your smartphone battery drains so quickly when running AI applications, while your brain, this incredible 3-pound organ, can process complex information all day on roughly the same energy as a dim light bulb? That fascinating disparity is exactly what's driving one of the most exciting frontiers in computing today: neuromorphic systems and brain-inspired artificial intelligence. In this episode, we'll explore how scientists and engineers are essentially reverse engineering the human brain to create computers that think more like us, and why that matters for everything from your smartphone to self-driving cars to the future of medicine. So get comfortable, because we're about to get neural. Let's start with a quick comparison. Your conventional computer, whether it's your laptop, smartphone, or even massive supercomputers, all use what's called a von Neumann architecture. Named after mathematician John von Neumann, this design has separate areas for memory storage and processing. Data constantly shuttles back and forth between these areas, creating what engineers call the von Neumann bottleneck. Now think about your brain for a second. You don't have one area that just stores memories and another that just processes them, right? Your brain combines these functions. When you recognize a friend's face, you're not sending data from your memory module to your processing module. It's all happening in the same interconnected neural network. This fundamental difference is why your brain can do amazing things on just 20 watts of power, while a supercomputer doing similar tasks might need thousands of watts. You might be thinking, if the brain's design is so superior, why didn't we build computers this way from the beginning? Well, that's a great question. The truth is, silicon-based electronics developed along a path that was easier to engineer with the technology available at the time. We're only now reaching a point where we can realistically mimic the brain's architecture. So what exactly makes neuromorphic computing different? Let me break it down into 3 key features that make these systems special. First, there's the architecture itself. Neuromorphic chips like Intel's Loihi 2 or IBM's True North use what we call memristive crossbar arrays, or event-driven circuits, that essentially co-locate memory and processing. This eliminates that bottleneck I mentioned earlier. Some of these systems can process information 1,000 times faster than conventional GPUs while using a fraction of the energy. We're talking about energy efficiencies that are 10,000 times greater in some cases. Second, there's how these systems handle information. Traditional computers use continuous values to represent information. Think of it like a dimmer switch that can be set to any brightness level. But neuromorphic systems use spikes of activity, just like neurons in your brain. A neuron either fires or it doesn't. It's binary, like flipping a light switch on or off. But the timing of these spikes carries tremendous information. This method is called spiking neural networks, or SNNs, and it's incredibly energy efficient. The third special feature is how these systems learn. Your brain uses something called spike timing dependent plasticity, or STDP. Basically, connections between neurons that fire together frequently become stronger over time. This is why practice makes perfect in human learning. Neuromorphic systems implement similar plasticity mechanisms, allowing them to learn from experience rather than just being programmed with fixed rules. Can you imagine what this means for a robot trying to navigate a new environment, or an AI assistant trying to understand your preferences? Instead of needing massive datasets and energy-hungry training sessions in the cloud, these systems could learn on the fly, adapting to your specific needs with minimal energy consumption. Now let's talk about where these brain-inspired technologies are already making waves. First up, autonomous systems and robotics. One of the biggest challenges for self-driving cars is processing visual information quickly enough to make safe decisions. Event-based vision sensors inspired by the human retina don't capture full frames like a conventional camera. Instead, they only register changes in the visual field. This drastically reduces the amount of data that needs processing. Tesla, for example, has been testing prototype systems that can process high-definition video inputs rapidly, improving detection capabilities even in challenging conditions like rain or fog. And they're doing it with much less energy than traditional computer vision systems. In healthcare, the applications are equally exciting. Have you ever worn a fitness tracker that needed charging every day? Imagine instead a medical monitoring device that could run for weeks or months on a single charge while continuously analyzing your vital signs. That's becoming possible with wearable neuromorphic processors. The NeuroPatch platform, for instance, has been effective in early arrhythmia detection. By processing heart rhythm data locally rather than sending everything to the cloud, it can alert users to potential problems faster while maintaining privacy and using minimal battery power. Perhaps most fascinating are neuroprosthetics, devices that interface directly with the nervous system. Traditional prosthetic limbs follow programmed movements, but neuromorphic controlled prosthetics can adapt and learn from ongoing feedback, creating more natural movement patterns for users. The difference is like comparing a pre-recorded message to an actual conversation. Of course, we're not quite ready to build a full artificial brain just yet. There are some significant challenges standing in the way of widespread adoption of these technologies. The scale problem is perhaps the most obvious. Your brain has approximately 86 billion neurons and trillions of synaptic connections. The largest neuromorphic systems today, like Intel's Hollow Point, scale to about 1.15 billion neurons. Impressive, but still orders of magnitude away from matching the brain's complexity. Then there's the standardization challenge. How do you compare the performance of these novel architectures to traditional computing systems? It's like trying to compare apples to, well, brains. The industry needs standardized benchmarks that account for both task complexity and system design. Initiatives are underway to develop these metrics, but we're still in the early days. There are also important ethical and security considerations. As these systems become more brain-like in their capabilities, questions arise about safety, security, and responsible use. Spiking neural networks could be vulnerable to new types of adversarial attacks that we haven't even considered yet. How do we protect systems that learn and adapt in ways that might not be entirely predictable? Looking to the future, researchers envision what they call symbiotic neuro-AI ecosystems, essentially tightly integrated networks of computational modules that reflect specific brain regions, working together as a cohesive system. We're seeing tremendous growth in this field, with the market for neuromorphic technologies expected to expand significantly in the next decade. As we wrap up today's episode, I want to leave you with a thought that I find particularly fascinating. For decades, neuroscience has benefited from computer science, using computational models to better understand how the brain works. Now, we're seeing the relationship come full circle, with neuroscience informing the next generation of computing. This cross-pollination between disciplines is creating technologies that could fundamentally transform our relationship with machines. Imagine AI systems that don't just calculate but intuit, robots that don't just follow programming but adapt and learn, and medical devices that understand your body almost as well as your own brain does. The brain has had millions of years of evolutionary fine-tuning to become the most energy-efficient, adaptable computing system we know. By taking inspiration from its design, we're opening up new possibilities that go far beyond what conventional computing could achieve. If you're as fascinated by this topic as I am, there's never been a better time to pay attention to this field. The convergence of neuroscience, computer engineering, and artificial intelligence is creating one of the most exciting frontiers in technology today. Before I sign off, I'd love to hear your thoughts on brain-inspired computing. Do you think these technologies will transform our devices in the next decade? What applications are you most excited about? Drop a comment wherever you listen to this podcast, or reach out on our social media channels. Thanks for joining me on AI Unplugged. I'm Nova, and I'll catch you next time for another bite of the future.